So in this session, we will see the how the current we can find out the current equations. So you can see here the current equations in conductor wire we can find out using this equation, that is J is equal to Q mu and E. Similarly, current we can find in the diode, that is I is equal to I naught exponential of eta Vt minus 1, we will see. And the current in your BJT equations, you can find I is equal to IC plus IB. And the current in MOSFET you can find out using the ID is equal to K VGS minus VTH whole square, right? So we will see in this session that how can we find out the currents in all these semiconductor devices, including the first one is your conductor wire, right? Okay, so I welcome you all to the Spark Research YouTube channel. This is Dr. Veer Chandra, Assistant Professor in the Department of ECE. This session is especially dedicated to the Electronics Devices course, and in this session we are going to talk about the current for the different electronics devices, right? So this is important for your gate as well, so because it may carries the marks in between 6 to 10 marks. And if you will look into the syllabus for the gate, then definitely you will find all these four devices in your syllabus, right? Okay, so let's go first. How can we find out the current equations in our MOSFET, in our conductor wire? So in conductor wire you can use this equation. J is nothing, J is your current density, that is equal to I by A. That is suppose the how much current is passing through per unit area, right? So that is the J only. Just so J you can find, that is N is the number of electrons, right? The charge carrier, that is charge density. So number of electrons per unit volume, right? For unit volume means per unit centimeter cube, something like that, or the meter cube. And Q is the charge, that is the 1.6 into 10 to the power minus 19 coulomb for one electron, right? So first this one, and then mu is the mobility, right? So mobility, that is how much electron is the electron is faster moving inside your conductor wire. And electric field, that is E is your electric field due to the application of the some external battery voltage. So here basically free electrons are there in the conduction band, and then electrons are moving. So how much electrons will move, that will tell you the exactly the amount of the current density, that is J. So that is why J will depends, that is current density will depends on the charge, that is number of electrons, then the charge of the one electron, then the velocity of that electron, and then external voltage that you have applied, right? So let's see in the details. So first, why will it the pass through the conductor wire? Because definitely we are going to supply the some voltage. So because of that, electron will start to drift from one into another end, right? So that is the reason. So let's see here. So first, exactly what is the relation in between the current and current? So Q is equal to, you can use IT, right? So Q is nothing. Suppose number of electron is N and the charge is Q, so N into Q, that is total Q. And then Q is equal to IT. So you can write I is equal to Q by T, right? Similarly, you can also write your T. T is nothing, the time taken to cross that particular the position for any electron. So that you can write V divided by L. V is your drift velocity of your electron, divided by the L, that is the distance, that how much the electron is covering, right? So because you can write the T, you can replace your T is equal to L by V. That is the very simple equation. And then for the current density, we can write down the current divided by the area, that is per unit area, right? And now we are going to replace this J, that is J is equal to I by A. So this quantity divided by A. So now your current density will becomes your N Q V, that is drift velocity, and divided by L into A. Now check this N, that is the number of electrons, and divided by L into A. L is the distance and area is the cross sectional area, right? So L into A will be the total volume of your cylinder, right? So N, that is total number of electrons, and divided by the volume, that will give you the number of electrons per unit volume. So let's take it as a small n, and so your small n, you can consider it n divided by the La. So your current density now what it will becomes, your n divided by La is equal to n, and the q is the charge only, nothing else, and v is the velocity of your drift, velocity of your electron, right? So you can also write your J is equal to n q v, and that is also it can be written as rho into v. Now we know one relation, v is equal to mu into E, right? So v is drift velocity, can be written as the mobility into the electric field that we have applied across this conductor wire. So now if you will replace this v in this equation, J is equal to n q v, so finally you will get J is equal to n q v, right? And so if you will replace the value of v, then you will get n q mu and E, right? So n q mu is a constant, right? That you can call it as a conductivity. So conductivity can be written as, that is sigma can be written as n q mu, and so you can also write J is equal to conductivity into electric field, that is E. So this is the final current equation derivation, right? So you can use this current equation directly, that is equal, J is equal to n q mu E, right? And sometimes the questions may ask to find out the conductivity. In that case you can use sigma is equal to n q mu. Sometimes resistivity may also call, that is resistivity is the reverse of the conductivity, right? Okay, now we will see the another equation, another semiconductor device. So this is a PN junction diode, right? So here all of you are aware that in PN junction there is a P type of semiconductor device and there is a one N type of semiconductor device, right? So in N type of semiconductor device, a number of electrons are majority carriers and the number of holes are as a majority carrier in P type of semiconductor. So at the junction in the, if you bring closer to each other to your N and P type, then what will happen, there will be the depletion region that will form. And here is the characteristics. In forward biased, your current amount of the current will be very high if you will apply the voltage greater than the your V right V cut in voltage, and in reverse direction the amount will be almost negligible, almost zero, right? So the amount of current, how will you find out? So amount of current you can find out using this equation, I is equal to is, that is the your saturation current, and exponential function that is q into v divided by the eta vt minus 1, right? You can also write exponential function of v by v eta vt minus 1, right? And so here eta can be written as 1 for normal germanium diode, and it may be 2 depending on the different cases, right? For practical also. Okay, let's see. So how can we find out the current in the PN junction diode, right? So first here, if you will look carefully, then you can see. Actually, I got these, the information, these images from the Milman Halkia's book. So if you wanted to go through that book, you can go through, right? So that is the one of the base book. Okay, so here let's see here the how the electrons at the PN junction only, how we can write. So here we are trying to write x is equal to 0, and here it is the how many numbers of electrons will cross. So number of the electrons that is will participate in the diffusion, that will be your the total amount of the current. So the in the P type of here actually doping is very high inside the P type, and the doping is a little bit lower compared to the P type in the N type, right? So here the hole diffusion, that is how many holes are going to diffuse. So in N type it will consider as the electrons, and in P type it will consider as the hole, that is how many electrons are crossing, right? So the hole and the electron current diffusion components versus the distance in a PN junction diode, the P side is much more heavily doped as compared to the N side, right? So let's see here. So we'll find out the total diffused current at the at the junction x is equal to 0, right? So first of all, you can write this equation I, that is Pn at x is equal to 0. We are considering at this junction only, right? So A Q D P divided by L P, and Pn 0 minus of P of Nx, right? So here actually these equations you can get it from the 2.48, the previous equations, with the help of the diffusion current. This is the diffusion current only, nothing is inside your p type of the material. So how you can calculate. So area is your A is your area, Q is charge, D is diffusion constant, and LP is your diffusion length, and Pn at 0 position, and Pn at the normally, that is how many electrons will cross, right? So in our if you will see, then here from the Boltzmann relationship, it seems reasonable that P and O should depend exponentially upon V, as you know, the and how will it depend. So P and 0 will be, so you can write P and O and exponential of V by Vt. So V is your voltage that you will apply across the junction, and Vt is the thermal voltage, that is nothing, that is Kt by Q. So almost the value is fixed, that is if you will calculate, then Vt will comes almost 25 or 26 millivolt, right? So the relationship that gives the whole concentration at the ease of the end is and region, that is x is equal to 0 just outside the transition region in terms of the thermal equilibrium, minor carrier concentration far away from the junction, and the applied potential V is called the law of the junction, right? So the total diode current here, if you will substitute the value this P0 into this equation, that is 3.3, you will get this PNO at equal to AQDP and PNO LP, and this is exponential function V divided by Vt minus 1, right? So the electrons crossing the junction at x is equal to 0 from right to left constitute a current in the same direction as hole crossing the junction from the left to right, right? So hence total current I will be at x equal to 0 will be I of Pn 0 and plus of I of n P of 0, right? Crossing from right to left and left to right. Since the current in the same through the series I is independent of x and is indicated as a horizontal line, so expression you can directly modify from here, that is I is equal to I naught, these terms will be I naught, and then exponential function V by the Vt minus 1. So this is the final current equations, and further this current equations it has been modified later, and so here we introduced the one eta term, that is I is equal to I naught and exponential function V divided by eta Vt minus 1, right? So this is the important current equations that you should remember. So we will continuously use this current equation to find out the amount of the current inside your diode. So I naught is the reverse saturation current, which is mostly given. Otherwise, you may calculate using this AQ dP constant Pno divided by the L of P. L of P is your diffusion length, right? Okay, so now we will see the some more current equations inside the BJT. So here BJT is nothing. This is three terminal devices, that is either combination of PNP or combination of NPN. From construction point of view, your base terminal should have the lesser width, and the major current equations you can see here, right? So actually the current equations in BJT is mostly related to the diode equations only, because you can find, like you can consider it as a two junctions diode only, PN and NP, right? So I is equal to IC plus IB. So total current will be IE is equal to IBN plus IC. And similarly, another equations, IC is equal to beta IB. This is one of the important equations. And also you can write alpha is equal to IC by IE. Normally alpha should be 1 and beta should be in the range of 100, 200, something like that. Okay. Alpha you can write beta divided by 1 plus beta. This is also one of the important equations, right? And I is your emitter current, IC is your collector current, then applied voltage that you are applying, that is VCB, that is input voltage, and VC, that is output reverse direction voltage that we are applying, right? And so beta is also called the current gain, and ideally it should be very high. Alpha is ideal factor, it may be equal to 1, right? So let's see some more details about the BJT. So PNP type of the diodes is here. Current emitting current, that is IE, and base current, so total IC. So you can see here. So IB is equal to, so this is your output characteristic. So typical common emitter output characteristic. So here that we are going to find out the collector current with respect to the VCE, that we are applying collector VC, that is across the collector. So whatever the reverse reaction voltage we are going to apply, correspondingly the current the correspondingly respect you can find out the current with respect to variation in VCE, right? So IC you can find out using this equation also, ICO divided by 1 minus alpha plus of alpha IB divided by 1 minus alpha, right? Beta can also be written as almost equal to alpha divided by 1 minus alpha, and IC can be find 1 plus beta ICO plus beta IB. Normally IC will be beta IB, right? So this equation you can also use to establish the relation in between IC and IB, right? And here is your input characteristics. So this is the input characteristic for your PNP germanium junction transistor. Here whenever you are going to vary the VBE, so correspondingly you can find out the variation in base current, that is IB, right? So this will be almost equals to your simple diode. Okay, we will see the now lastly we will talk about the MOSFET current equations, that is this equation is very famous. ID is equal to K. K is nothing mu cox WYL WY twice L exactly, and VGS minus VTH whole square. So this equation will be valid only for the the active region, that is the after saturating, not in the linear region. So in the linear region this will be ID equal to K of VGS minus VT minus VDS and minus of VDS whole square divided by 2, right? So we will see both the equations and we will find out the equation. So from construction point of view, your substrate is there, then the gate is there, drain and source is there, and here is your gate, right? So ID is your drain current, that is the amount of current will pass through from drain source to drain, and VGS is the gate voltage, that will be the that will be consider as the to open this to create the channels here, right? So that will helps to create the inversion layer in this region. So VT is the threshold voltage, right? So that is the minimum required voltage to create the inversion layer, right? And here parameters are that mu cox is your the capacitance of your oxide layer, then W is the channel width, length L is the channel length, right? So let's see how to find out the current equations in the MOSFET. So this is your MOSFET here, and source and drain is here, so gate voltage is here. So whenever we are applying the gate voltage, correspondingly to that, actually your V voltage will vary, right? So voltage directly it will not drop from Vs to 0. So it will degrade the slowly, and so let's find out the variation in the voltage. So let's consider the variable voltage, that is Vx. So Vg minus Vs we can write, that is VGS, and we can also add plus VC and minus VC, right? So the VC, that is at this point what is the voltage, so we can write VG minus VS, that is VGS, and VG minus VC, that is VGC, and now VC minus VS, right? So VC minus V of S, so the variation, that is your variable, right? So this is our target to find out here. So actually the voltage that we are applying across this gate and to source, so that is your VGS, and another voltage we will apply D to S, drain to source, right? So let's find out the capacitance. So VGS will be, we can write VGS from here, VGC plus VX, or VGC we can write, that is VG and C. This voltage we can write VGS minus VX. Why are we trying to find out the voltage across this VG and C? Because this will, the with the help of this voltage only we can find the amount of the charge across this capacitor. Why? Because this will, the SiO2 layer will act as a capacitor, right? So let's find out. So Q is equal to V into C. So VGC across this voltage that we are applying, and capacitance, let's suppose the capacitance of your SiO2 layer is COX, right? So now we replace the value of VGC from here, VGS minus Vx, put it here, and you will get the total charge which will accumulate in the inversion layer, right? Also, the total charge will be equal, actually due to the drift and plus diffusion. So mostly diffusion, amount of the diffusion is very less here. So directly you can consider this drift, right? So if you will consider it, then you can write J is equal to because of the drift we have already calculated in the beginning of this slide, that is J is equal to Q mu and E, right? So just write down Q mu and E, and E we can write dB by dx, right? Electric field is equal to nothing, dB by dx. Then remaining terms are as usual. Now J we can write mu cox and VGS minus VT. Just you can replace this VGS minus VT, and you can add one more term, that is threshold voltage, because this is required to create the inversion layer, and then dV by dx. Now integrate this equation, J into dx and then these terms into the dV, right? Because only the Vx is going to vary from 0 to your V of GS, right? VDS. So 0 to VDS that you are applying, and the channel length will vary from 0 to L. So that is the amount of the current. So J of X into dx and then this term into dV. So integrate it, you will get the equation J of N into L, that is mu cox VGS minus VTH V minus V square by 2, and that is the value you are going to put from 0 to VDS. So finally, equations for linear region means if a channel is forming in between drain to source, then in that will be mu cox WIL VGS minus VTH VDS minus of V square by ds by 2. Now if you will further put the value of VDS is equal to VGS minus VTH, in that case your equation will becomes ID is equal to mu cox WIL and VGS minus VTH whole square, right? So the graph for the IV characteristic for your MOSFET is almost similar to the BJT, right? So you can check in the previous slides. So that's all in this session. Thank you to join the sessions. We'll come with some questions related to this. Thank you.